to introduce Professor Mikhail Khovanov from Johns Hopkins University. He's going to talk about SL3 web categorification.
Thank you. It's a pleasure to be here again. And the goal of this impromptu talk is that I found out that there was a visiting group here working on cluster algebras and related things. And I wanted to tell you about codification, because webs are intrinsically related to cluster algebras. Webs admit this codification, where instead of before a web, say, your boundary is an element of a vector space quant of invariants, and sometimes a product of representations. SL3, for instance, that's before codification, and that goes back to the work of Greg Kuperberg on spiders for rank 2 the algebras. But there's a kind of some upgrade of this construction where a web with boundary is not just a vector in some vector space, but it's an object of some category. And there are various versions of this category, but it could be a web could give you a projective module over some very special finite dimensional algebra, very special finite dimensional algebras. And you see this algebras throughout, for instance, modular representation theory of suitable finite groups. If you take suitable blocks of finite groups and finite characteristics, you might find the same algebras, but appearing in modular representation theory, you see them as blocks of cyclotomic KLR algebras, and you see similar categories studying coherent sheaves on Quill varieties, and in many other contexts. So this is the goal is to explain how this verification procedure goes, and let me remind you about SL3 in webs following Kuperberg. So we look at planar travelling graph at the build out of elementary pieces. So they're oriented, and every vertex is an in vertex or an out vertex. And this has a standard meaning in the story of SL3 webs, as represents an element in the tensor in the space of invariants of a tensor product of 3 fundamental representations of quantum SL3. So this is Kuperberg SL3 webs, and his rules for simplifying that first webs are planar. So such planar travelling graphs, which may also have circles. So his rules are simplify circle to quantum 3, which is the quantum dimension of the corresponding representation. So these are the other two rules. If you see a region which has two sides, a diagon region, you can simplify it and say it's quantum 2 times a simplified web. Quantum 2 is Q plus Q inverse. And a square region can be simplified using this decomposition. So this is standard. This is Kuperberg spiders for SL2, the algebras paper. And then if you have a web gamma, it's invariant, let me call it P of gamma. It lives in Z plus, Q inverse. So it's a Laurent polynomial in Q with non-negative integer coefficients. Non-negative is the key. And this extends to an invariant of links using these rules that crossing, the two types of crossing, is decomposed as a linear combination of the invariants for these two diagrams. Again, these are just rules in the space of intertwiners from the tensor square of representation V into itself. And for a link L, it's invariant P of L, lives in Z Q inverse. So here it's no longer positive. Any coefficients can appear, while here it's positive. Then for codification, it's often non-trivial. So if you see something positive and you're trying to clarify it, it's an indication that codification is not a complex, but it's just a single vector space or a single abelian group. So here, because we see this lives in Z plus Q inverse, you may hope so. Let's see the so what was the original motivation? We look into categorify this invariance of links, Morphisms of invariant of links. But there's this intermediate object, a plane of web gamma, but it's invariant in some sense it's easier. It only lives in Z plus, all the coefficients are positive. So we can try to lift this polynomial to some kind of state space or homology assigned to gamma such that it's degraded abelian group or a vector space, and such that the graded dimension of H gamma is the polynomial of gamma, is the invariant P gamma. So we kind of want to simplify, reduce the complexity of the construction. Let us first worry about these planar graphs and verify the invariant, and later worry about links and their invariant. So how can we? So we're looking to upgrade these numbers, quantum 3, quantum 2, and these inductive rules into the next level of structure, so that, for instance, instead of a number assigned to the circle, we want to assign a graded vector space of this graded dimension, 2 squared plus 1 plus q minus 2. And we want this construction with assignment of the gamma sign homology of state space H of gamma. We want this to be functorial. So functorial in what sense? For instance, later, assume we already done this. Assume we already get homology groups, H gamma. Then we want to move on to links. So to links, you want to build more complicated groups assigned. And for this, we'll need to lift, one possibility would be to look at these scale relations for links, which now have minus signs. And we would want to convert these scale relations to long exact sequences, saying that homology of these three links, or these three generalized links with trivial vertices, they fit into their part of the long exact sequence of homology groups. And again, Q should be just shift in the grading, the extra grading. And to have a long exact sequence between these three groups, you would want to have homology for these two diagrams, but we also want to have a homomorphism from one to the other to fit, to build, to use in this exact sequence. And this homomorphism, perhaps it comes from some cobordism between these two graphs, because you can imagine a cobordism where these two edges approach each other and merge into this edge. So that a cobordism. Enjoy the cobordism. This is web gamma null, this is web gamma 1. We can build a cobordism from gamma null to gamma 1. And so I call such cobordisms forms cobordisms in webs. So we want the sphere to be factorial in the sense of we want to assign to a graph a state space or homology groups, and to a cobordism from graph gamma null to gamma 1, cobordism S, we want to assign a map HF from H of gamma null, H of gamma 1. Cobordisms, it could have, they're expected to have this kind of singularities where, so here we have a vertex where three edges converge, and here, so we should have at least that singularity times the interval where the three facets merging into a single edge. So, so how can we build such a theory? So you see here, well, as a special case of this cobordisms, we should probably have cobordism merging two circles into one, or splitting a circle into two. Just these are forms of cobordisms with no seams, with no singularities. Well, we want to have them as a special case. But this means that homology of a circle must be a commutative Frobenius algebra. because we must have the multiplication for multiplication, unit and co-unit. So, and there are very few such structures on this abelian group of vector space. So let me just suggest that homology of a circle should be z of x modulo x cubed, where degree of x is 2. Degree of x is 2. Then we have basis. Graded range or graded dimension is 1 plus q squared plus q to the 4th, which is almost what we need because we want this answer. We want this graded dimension. This is almost what we need. We just need to scale it. So let me call this homology A. So z of x modulo x cubed. But just for convenience, I'm going to shift the degrees down by minus q. So I'll assume that the unit element is in degree minus q, x in degree 0, x squared is in degree 2, just for convenience. And then you can check that if you have some cobordism S, this assignment, this Frobenius algebra, because of the grading, the induced map, it induces a map between tensor powers of this algebras given by the number of circles on the boundary of the cobordism, and this map, what we call it h of s, and it has degree h of s. You can check it's minus twice the point characteristic of the surfaces. So there's a nice formula for the degree as a function of s. So fine, but let's go further. So now the next graph that we can have is this graph. So this actually has vertices. This has vertices. So for this graph, gamma, so we want, let me call it P. We want homology of gamma. And it's, what is the Kuperberg invariant? P of gamma is quantum 2 times quantum 3. Because quantum 2, because we remove a diagonal region because of quantum 2. And then we'll start with a circle. So it is quantum 3. And we already, for the circle, we already picked up this quotient, which we can identify the homology of CP2. So then you can guess that adding this additional 2 should correspond to expanding from CP2 to the flag variety of C3. So let us take the P to be the homology of the variety of flags, FL3. FL3 consists of flags, let me write it as 0. Let me write this L1, L2 in C3. A line chain in C3. And there are various ways to go from FL3, forget part of the structure, map it to CP2. You can forget L1, you can forget L2, if you have a Hermitian metric, you can take complement, etc. So there are several ways. And in fact, there are several ways to reduce from this diagram to a circle, which is quantum 3. You can simplify this region, or you can simplify this region. Or if you think of a graph gamma being on the 2 sphere and not on the plane, you can simplify the outside region. In fact, that matches the various ways to map flags into CP2. So this is, this of course, this has this standard presentation. Z x1, x2, x3 modulo the ideal of elementary symmetric polynomials, x1 plus x2 plus x3, x1, x2, x1, x3, x3, and x1, x2, x3. The standard presentation. So you can sort of think about this x1, x2, x3 corresponding to the 3 edges. Then you notice that this is a commutative thing. So what should this ring structure correspond to in the language of webs and cobordisms. So you can, this web has a line of symmetry. So you, let me draw it here and draw it again. There is a symmetry line of this gamma. And there's a cobordism where we match these two pieces against each other. Cobordism into this diagram, which is gamma. Just kind of cobordism, so we remove this piece across half space to match, to get to couple to the opposite piece. So it's a slightly more refined version of the cobordism from two circles into one. Cobordism from two circles into one, where this piece is matched against its reflection.
So yeah. What is the shaded area? Some in the picture of the flow.
Yeah, so let me draw it here also. Let us start with a copy of gamma and another copy of gamma. And take a cobordism, it's Pan's cobordism, but we kind of sort of single Pan, so we're adding space, we're adding a plane in the middle. So if you want, you can just start with the Pan's cobordism from two circles into one, and then attach the plane with this boundary. So we just kind of we're coupling this part of the diagram against this part of the diagram. Some kind of merge. So this is a special line, that's a seam line. So these are also seam lines. Sort of in our factorial theory that we're looking for this kind of, so this explains why the state space of this diagram should be an algebra, because we have this multiplication which is associative, and we also, for this multiplication, we also have the unit map. For the unit map, we should take the graph and look into sort of this kind of cobordism, this kind of form, where this is a seam. So this kind of form, it just matches one half of the graph by rotating it all the way to the opposite half. And rotating this half of gamma to the opposite side. And this is going to be an element 1. This is going to represent element 1 in our homology of the flag variety B. And so if you take this cobordism and couple this to one of its legs, you get the identity. You can just cancel these two critical points against each other, so you get the identity map. So this acts as the unit element. And if you look at it in the opposite way, as same cobordism, but used as a cobordism from gamma into nothing, into the empty graph, that's actually a multiplication. That's a trace map. So it's map from E to the ground A to Z, which is the homology of the empty graph. So this sort of kind of explains what we want. Again, we want a graded Frobenius algebra with this graded dimension. There are very few choices. So if we kind of building up from CK2, we can pass to the flag variety. Take this algebra, so sort of it matches. I mean, it matches what we want. Then, so it's convenient to also introduce to encode this X. What we encode it by using a dot on the form. So I'm going to put a dot. So this is going to be element 1. In A, this is denotes element x, and A, 2 dots denotes element x squared, and 3 dots is 0. So just like a way to encode. And we'll need the Frobenius algebra structure on A, which is our homology of the circle. So we're going to take the Frobenius algebra, where the trace map is non-trivial on the top degree. Just I think for convenience I take -1, so it doesn't matter too much. But as a result, you'll have in the Frobenius algebra, you always have a decomposition. You can take identity map, identity cobordism, describing identity map from the Frobenius algebra to itself, and decompose it as a sum of basis vectors coupled to dual basis vectors. So this is just an example of the standard decomposition of the identity map of a commutative Frobenius algebra. You can always write this down. And so here in our calculus, we agree that again we have this singular seam line or singular line, and the method that we encoded unit element using this cobordism from nothing into the graph gamma. But let us also agree that we can put dots on various facets of this cobordism, and we agree that dots will encode monomials. So for instance, this responds to x1 squared, x2, no x3. So dots. And then in particular, if you apply the trace, if you close this up, of this closed form, now this form describes the trace of the particular monomial you chose. Our monomial was x1 squared x2. This is the trace. And in fact, depending on the normalization, this trace is going to be 1 or -1, so let's pick 1. For other examples, say epsilon of x1, x2, x3 is, well, okay, this is, let me just put here, say x1 cubed. So this is 0. So you can check that these are the only possible non-zero monomials, xi square, xj. Everything else gives us 0. And then, so the idea is, in the SL3 case, that's all you need to know to build H of gamma for any gamma. You just need to know these two algebras and their interrelations. And this is done using so-called universal construction. For this, to define it, so we start with gamma. From gamma, let us define this free space of gamma, the modulo gamma, as look at all the forms that bound gamma. So look at all the forms with bounding gamma. Forms F, which means P of F with gamma, and define the symbols to be in this K-Billion group, everything with bounding gamma. And now define a bilinear form on this group as follows. Bilinear form. Take two forms. We bound the gamma at 1, at 2. So we build them together on gamma. Say F1 bar F2. Take two forms, you bound the gamma, you do one on top of the other. So we get a closed form. Closed form has no boundary. It consists of several circle seams. So this becomes circles. It consists of stuff in between them. So there is this, so hygienic surfaces with dots floating everywhere. We have this closed. So when you do from F2, you get this closed from F. And we evaluate it to a number using these rules. So every time we see a surface of genus higher than 0, we do a surgery. Here we see a surface with surgery. Now we can also do surgery. If you look at this singular circle, we have three facets of three regions coming into the circle from the three sides. Also along the circle, we see these three regions. So we can just do a surgery, individual surgery, near each of the three regions, near the yellow circle. So in other words, we cut off everything here from the circle. Possibly at the cost of, when we do this, when we'll have the circle, and we'll have a disk here, possibly with some dots. Because when we do the surgery, some dots appear. Then, if this, maybe this has some genus, so we can also cut this off at the cost of maybe having some dots here. And cut the third piece off at the possibly because some dots. Then when we cut off, that we evaluate using TQFT for cohomology of CP2. Then what we're gonna have is something we already evaluated, and a bunch of this shapes. We call it theta form. Theta form, it consists of a singular circle with three disks attached to it, possibly with some number of dots. And if there is N1, N2, and 3 dots, and then we just apply the trace map epsilon, the trace map on cohomology of the flag variety applied to x1 and 1, x2 and 2, x3 and 3. And that's the evaluation of this blob. And this is almost always 0 unless it's like Q 1 0 in some order. And it's possible. But in this way, this gives us this kind of procedure, the surgery allows us to evaluate any closed form into evaluate to an integer, to an element of Z, to an integer. So closed form get evaluated to an integer. So F get evaluated to bracket of F in this way. So again, we're just using two Frobenius algebras, cohomology of CP2 and cohomology of the flag variety and FL3 to evaluate any such closed form with handles, dots, single circles to Z. And so the universal construction does the following. So you define the state space, define H of gamma to be the free modulo on gamma, anything which bounds gamma, and there is a combinations modulo of the kernel of this bilinear form. So we just look at everything that all the forms that bound gamma, but in the linear combinations, but we say if you have a linear combination such that no matter what you put on top, you know, you get 0, means the whole thing is 0. So we have a theorem. And there is some grading because a dot has degree 2, so you can set up to make it graded. So theorem H of gamma is a graded, is a free graded abelian group. And the graded rank H of gamma is the Kuperberg invariant P of gamma. And so part of the theorem is that there are inductive, we can define this H inductively by saying if you have H of a circle union with some web gamma, that's isomorphic to the state space of gamma, tensor our A is again it's Z of x mod x cubed is the cohomology So the key thing is to prove the inductive direct sum decompositions, that homology of a graph with a diagonal, homology of a graph with a diagonal facet is homology of a simplified graph with a gradient shifted by 1 plus homology of a simplified graph with a gradient shifted by -1. So this verifies the Kuperberg relation that the invariant P of this graph is equivalent to P of this graph. We can verify Kuperberg relations in this way. And 3, that homology this graph is isomorphic to homology of this graph plus homology of this graph. So kind of what is going on. So first you derive this inductive direct sum decompositions. So that's the key part. You derive this inductive decompositions using, for instance, for give you an example for how do you check that this graph, the state space for this graph is the sum of 2 copies of the state space for this graph. What you do, you build cobordisms. You say, I want the cobordism from this graph into this graph, this form. So I go from this graph upstairs. And now the cobordism back. Minus sign. And so you just set up these cobordisms. And you check for the cobordisms for the induced maps alpha 1, alpha 2, beta 1, beta 2. You compose these maps and you check that you do alpha, for instance, if you go beta 1, alpha 1, beta 1, alpha 1, you get the identity for this graph. So beta 1 means you go from bottom to top. You go from this line to this graph, then you go back. That's identity. Beta 1, alpha 2 is 0. Likewise, beta 2, alpha 1 is 0. Beta 2, alpha 2 is identity. And then that the other way, alpha 1, beta 1 plus alpha 2 and beta 2 is identity of this graph. Now, so you set up these forms that go between these graphs. And these forms induce maps, because this construction is factorial for cobordisms. This construction, if you have a cobordism from one graph to another, you can check whether it induces a map of the groups. So to get the decomposition 2, you set up this for cobordisms. It's kind of really just one cobordism, but sometimes flipped, and sometimes with a dot on an appropriate facet. And you check, for instance, saying that beta 1, alpha 1 is ident. It says that if you take a plane, and on this plane you kind of create some kind of a bubble floating thing, like this. It's a composition of these two. In this case, you put a dot on the back facet. But this evaluates to 1. So maybe I should put here somewhere. I should put a minus sign. Minus sign here. Here, but this is the same as just a plane. Saying that this form is equal to this form in this quotient. So you kind of just check this relation. So you need to you do some computation with forms, but this is how you establish this isomorphism. So this isomorphism is given by very specific forms between the source and the target. And likewise for this decomposition, you create forms from this graph to these two graphs, there's really just one form you can think of. It's a form that matches after rotations and reflections. There is just one form. So you match these 2 points, and you match these 2 points, and you connect them by the facet. That's a so this is the cobordism. This is the cobordism from this graph, from the square, into one of these two simple graphs. You can rotate this cobordism, you can reflect it, and then you can check that the 4 maps you can get by taking 4 versions of this cobordism. They give you direct sum decomposition number 3 down there. And then from 1 to 3, you reduce from the decomposition. You know that Kuperberg's simplifications allow you to get from any graph gamma to union of empty graphs. So that's how you get from. So using this, it shows you that homology of gamma is homology of empty graph, but taken p gamma number of times in the gradient sense. And homology of the empty graph is 0. That's easy to see. It is z using our definition. Represented by the empty form, the empty cobordism into the empty graph. So this is so this theorem. So given a graph, given a web gamma, given a SL3 web, so gamma SL3 web, we build H of gamma, graded abelian group such that its only characteristic is the invariant P gamma. And then, so from here you can build link homology by arranging these state spaces into complexes and introducing differentials. Standard. But another interesting thing is that you can load. Let me pause for questions.
Okay, how about the number 3?
Yes,
Here
yes.
in the dot in the square.
Yeah, number 3. So you have this web, and you have these 2 webs. So you construct maps back and forth. The maps given by the versions of this cobordism. So, for instance, so from here to here, you would go to the cobordism. Use this cobordism. From this diagram into here, and to get this map, just rotate this cobordism 90 degrees. Rotate it 90 degrees, and get this map. To get this cobordism, you reflect this cobordism about the horizontal plane. So you go to here. Schematically, that's the cobordism back from the square into the circles. And the rotations give you this cobordism. So, for instance, if you compute the composition with this composition, you'll see that this composition is a diagram where you have a bubble in the middle which bounds which lies on a single component. So in fact, the fact that this composition is zero is equivalent to the fact that this composition is zero.
Okay.
Or you just go from here to this region and back with no dots. If you have no dots, it's zero. And if you write down this composition, you'll see it's just a more complicated version of the same story, where now it's just that the seam, the circle looks more complicated because it's a composition of this thing and the other thing. But it's really just topologically it's the same as just this composition of these two. Yes. So from this way, it tells you that that it's a free abelian group of graded rank equal to the Kuperberg invariant. It also tells you that it's TQFT in the sense of homology of a disjoint union. It's isomorphic to the homology of gamma 1, the other gamma 2. So that follows from scaling relations 1-3. You just simplify everything to copies of nothing.
Can I ask very silly basic question?
Yes.
So your cobordisms are what you call foams,
Yes.
and foams mean, so they're not manifolds. So they're
not manifolds, they're singular.
What do you say?
Singular. We call them forms, so they're cobordisms, so they lie in R3. So for us, it's our webs lie in the plane, so cobordisms lie in R3, so they're forms F in R3 of very particular singularities, and working with SL3 is a big simplification because we don't have more complicated singularities. We just have this circles. We just have this arcs and circles with singularities. If you want to go to SL4, you will get more complicated singularities because now you can have vertices, which are singular. So the complexity grows, kind of jumps when you go from 3 to 4.
But do you like try to characterize by words what you mean by foam? So it's two-dimensional thing that has one-dimensional singularity.
Two-dimensional, let's say two-dimensional CW complexes embedded in R3 with prescribed singularities. So in this example, in this theory, we only allow trivial vertex times an interval. So we only allow these singularities locally. For SL4 and high, we'll have to allow vertices. So we'll have to do the case where singular lines we can merge into singular vertices, which makes it more complicated to evaluate these forms because you cannot just split every circle, every singular circle away from the others. So that's much harder. That was done by Robert Lodry and Robert Wagner in 2017. So for the case in some sense it's much easier.
So what's the difference your singular line and the line defect was the?
It's what's the line defects? It depends because I guess physicists often look at line defects, say on surfaces. Mm-hmm. That's a different kind of defect.
Right.
These are different defects. Sometimes, in some cases, so if you take a three manifold M3, if you take a triangulation T, and you look at the Poincare dual of T, that's a self-decomposition of M3.
Okay.
So it looks like a form. Mm-hmm. So another way to think is that forms, especially for beyond the SL3, for SL4 and higher, they are ignoring all the decorations. There's some decorations. Ignoring all the decorations and some other things, they are similar to two skeletons of the Poincare duals of triangulations of three manifolds. But also people encounter forms in 4D as well. So what happens? So when you look now at things with boundaries, so if you look, so in the Kuperberg framework, you can look at all the webs in the disk that bound a given sequence of signs on the boundary. So given a sequence of signs epsilon on the boundary, you can look at all the webs of gamma with boundary gamma and epsilon, modulo relations. And let me call this V sub epsilon. Now let me call it maybe O sub epsilon, Z if you inverse linear combinations of gamma, of such gammas modulo Kuperberg relations. So then, as we know that this O epsilon is an integral lattice in the space of invariants, SL quantum SL3 with USL3 invariants of the tensor power, tensor product of the fundamental representation and its dual. So in this case, this would be invariance in V tensor V, tensor V star, tensor V star. But this is integral. So there is a map from here to here which becomes an isomorphism if you tensor it with, say, U of Q over Z Q inverse. So size-wise, it's the same as the space of invariants in the tensor product of quantums of representations, but it's an integral form. It's over Z Q inverse. So and that's before clarification. After clarification, so we can have a category called Karoubi epsilon with objects. So for each gamma with the gamma epsilon, we have an object. Let me call it. Let me call it Q of gamma and Q sub gamma. It's an object such that home from Q gamma null Q gamma 1 is given by. Let me turn things around so that the webs live in the lower half plane. Pass from a disk to lower half plane, so webs in the lower half plane has the boundary on the x-axis. So define a category where the home is the state space of the gluing gamma null bar gamma 1. In other words, so take gamma 1, take gamma null, glue them together. So gamma 1, this is gamma null bar. So we glue them together to get a closed web that has a state space. It's a great practice. To define homes to be the state space of gamma null bar gamma 1. So the composition of morphisms in this category given by, so if we're looking at all from gamma 1 to gamma q, there should be elements of F gamma 1 bar gamma q. I would draw gamma 1 bar, take a reflection of gamma 1. And here there is some gamma q. So if I put them together, I have a cobordism which cancels gamma 1 against gamma 1 bar. So this cobordism going into gamma 2, gamma null bar. Cobordism induces a map. So H gamma null bar gamma 2. So, and this is our composition of morphisms. So in this way, we get a category with objects given by Kuperberg webs with a given boundary. Morphisms given by this construction, the composition of morphisms.
You have the two morphisms now as you have the construct.
this is just a symbol, it's just a category for we fix a sign sequence. We fix a sign sequence. So we take all Kuperberg webs with a given boundary. These are our objects, and these are the morphisms. And this is composition of morphisms. And then you can check if you can assume that gamma is non-elliptic. So it doesn't have any of these regions. It's non-elliptic. Then, because if gamma has a region of this form, you can reduce the corresponding object, say, to 2 copies of the simple object, or to a sum of simple objects. So you can keep reducing until you're down to non-elliptic webs. Now, so if you take, so we get an algebra for each sign sequence epsilon, we get an algebra A sub epsilon, which is the sum of H gamma, I'll just write gamma I bar gamma j, where gamma I gamma j over all non-elliptic webs at their boundary epsilon. So this is an algebra. It's a finite dimensional graded algebra. Often it's convenient to work over a field, not over Z. And then, so if you look at this algebra, you recognize it inside various structures and representation fields. So it's not semi-simple, of course. For the simplest cases for plus and minus, you just have a single diagram. You do it to itself, you get the homology of CP2, so the algebra A plus minus is K of X modulo X cubed. The homology of CP2. And for plus, it's an algebra with this kind of single generator. You couple it to itself, you get our algebra B, which shows the homology of the flag variety. Then beyond this, we get non-commutative algebras because now you have more than one basic web. So here you'll have an algebra built out of taking these 2 diagrams, doing them to each other, and for possible ways, each time take the corresponding state space. And this is multiplication. So it's reminiscent of. I think you can reconstruct it using coherent shifts on a suitable Q variety. But I'm not sure about the actual status of these results, but conceptually you can build these algebras by looking at coherent shifts on suitable Q varieties. Or by looking at other algebras and suitable blocks that appear in modular representation theory, or blocks of cyclotomic KLR algebras, etc. That's the idea. So this is a lifting of, so before we had this all 3 webs, and if we do webs with boundary, we get this space of invariants in terms of products of V and its dual, representation of condoms of 3. So that's before clarification. But now on the next level, we have this finite dimensional algebras, one for every sequence of boundary points. And the Grothendieck groups, they give us the space of invariants. So every non-elliptic web is an object, is a projective module, responds to a projective module over this algebra. So it would be, I think, very interesting to look at the kind of things that people do with webs in the context of, say, cluster algebras and see if there is any interpretation or any clarification of those statements in this setup. But of course, it's much harder to do computations here because we're dealing with forms. It's not web, so we have one-dimensional. Let me stop here. Thank you.